All right, kids, stoichiometry part 2, question number 8. If you have 55 grams of aluminum, you dissolve it into hydrochloric acid to completely react. How many grams of hydrogen gas will form? To do stoichiometry, we need a balanced chemical equation. So let's write the formulas. Aluminum goes into hydrochloric acid. To start, aluminum's a metal. Hydrochloric acid, HCl, is aqueous. Quick check on table J shows us that aluminum and hydrogen are both on the left. Aluminum is a metal. Hydrogen acts like a metal in these kinds of reactions. It's going to form cations. It is a cation here. But aluminum is higher. Aluminum will replace the hydrogen in solution. So we're going to do a quick switch. The aluminum jumps into solution with the chlorine, and the hydrogen pops out. We switched it. Now we got to fix it. Things to think about. First of all, hydrogen's a Hunkelbrief twin. It's got to be H2. Aluminum cations are +3, and chlorides are -1. So it's going to be AlCl3 in a 1:3 ratio and H2 gas. So aluminum chloride's aqueous solution. We can check table F. This is our skeleton. Now we're going to balance it. We're going to start out on the front. There's one aluminum, one hydrogen, 2 hydrogens. We need two hydrogens for the chlorine, and then back and forth a few more times till we get to this balanced chemical equation. Hopefully you know how to do that. This is balanced in a 2:6 to 2:3 ratio. 2 aluminums on both sides, 6 hydrogens on both sides, and 6 chlorines on both sides. Now, this is about aluminum and hydrogen. There's 4 parts to this, but we're only looking at grams of aluminum. We want to know about grams of hydrogen. It's about aluminum and hydrogen. The middle part, the HCl and the aluminum chloride, are not part of this problem. They're important, but we're only looking at aluminum and hydrogen. So the first thing we have to do is convert these grams of aluminum into moles. And how do we do that? Well, we start with this 55.0 grams of aluminum over 1, and we have to multiply it by the molar mass of aluminum. If you put your finger in box number 13, aluminum is 27 grams per mole. We don't use decimals in our class for molar mass. We round to the nearest whole number. So if we multiply this by the molar mass, 1 mole of aluminum is 27 grams. The grams cancel. 55 grams of aluminum is the same thing as 2.04 moles of aluminum with 3 significant figures. This question is about aluminum and hydrogen. So we have to compare the moles of aluminum to the moles of hydrogen in the second step, which is called the mole ratio. The mole ratio we're looking at is between aluminum and hydrogen, which is, of course, in a 2:3 ratio. 2 moles of aluminum react with acid, makes aluminum chloride, and 3 moles of hydrogen come out. But we don't have 2 moles of aluminum. We have this silly number, 2.04 moles. When we crisscross multiply, we see that this much aluminum, 55 grams, which is 2.04 moles, is going to be in proportion to 3.06 moles of hydrogen. The question's not moles of hydrogen, though. There's a lot of equal signs, right? You got to pay attention. You can't get lost. You got to write big. You got to use your units. 3.06 moles of hydrogen. The question is, how many grams? So in the last step, we're going to take 3.06 moles of hydrogen, which is our new starting point. We're going to multiply it by the molar mass of hydrogen. It's 2 grams per mole because it's H2, and the answer comes out to be 6.12 grams of H2 gas. This was a 3-step stoichiometry problem. The numbers were small, but this is as hard as it gets. 3 steps can't get any bigger. You need a balanced equation. You got to figure out what 2 parts you're looking at. In this case, we looked at aluminum and hydrogen. And then we had to do some fancy math to get moles, and then we had to take the moles of hydrogen and do some fancy math to get the grams of hydrogen. Question number 9. Aluminum and HCl. We'll use the same chemical equation. This time we start with 23.1 moles of HCl. How many formula units of aluminum chloride are going to form? Now in this, we're going to use the same exact balanced chemical equation. 2:6 to 2:3, right? 2 moles of aluminum, 6 moles of acid, 2 moles of aluminum chloride, 3 moles of hydrogen. In this problem, there's a couple things going on. First, we're looking at hydrochloric acid and aluminum chloride. We're not looking at aluminum and we're not looking at hydrogen. They're not part of this problem. Second, we're starting with moles. This is only going to be a two-step problem. This is actually smaller. This is actually easier in a sense. There's less parts. So we're looking at moles of hydrochloric acid, how many formula units of aluminum chloride set up. So we're going from moles through the tunnel to moles 2, and then once we get the moles 2, we'll go to formula units. First step we need is the mole ratio. Let's see what we got. The mole ratio of hydrochloric acid to aluminum chloride is a 6-to-2 ratio, but we got to think. 6-to-2. Are we going to change that to 3-to-1? 6-to-2, 3-to-1, simple whole number ratios. What do you think? Absolutely not. The balanced equation is in a 2-to-6 to 2-to-3 ratio. That's the simple whole number ratio John Dalton was talking about. We're looking at just HCl and aluminum chloride. 6-to-2 is fine. It's going to take care of itself. Don't be changing things. The mole ratio is 2-to-6 to 2-to-3. The part we're looking at is 6-to-2. HCl to aluminum chloride. We're not changing it. Stick with it. So here we go. We have 6 moles of HCl, makes 2 moles of aluminum chloride. But in this math problem, we have 23.1 moles. So we have to make a proportion. 6 is to 2, as 23.1 is to X. We set this up. How we solve for X? We have to cross multiply, and then we have to divide. 6X is equal to 46.2. We divide both sides by 6. And what is 7.70? Well, where is the X? Look, X is on the bottom. What's on the bottom? Aluminum chloride. And it's the mole ratio. So 7.70 moles of aluminum chloride are going to form in this reaction. If we use up 23.1 moles of acid, we're going to get 7.70 moles of aluminum chloride. Is that the answer? No, it's not. The question is how many formula units? So we have to take that 7.70 moles of aluminum chloride over 1. That's going to be our new starting point. And now we have to multiply it by what is the conversion factor to go from moles to formula units. 1 mole is equal to Avogadro's number. So we're going to multiply it by Avogadro's number of formula units over 1. The moles are going to cancel, and this is going to come out to be a crazy math problem. Let's just look at this. Don't do it yet. 7.70 times 6.02 times 10 to the 23rd. We're going to do the first 2 parts, the 7.70 times 6.02, the first 2 parts first. And we'll multiply the whole thing times 10 to the 23rd. So we're going to multiply those 2 numbers. It turns into 46.354 times 10 to the 23rd. With 3 significant figures, it rounds to 46.4 times 10 to the 23rd. And then you got to remember, you can't have a number bigger than 10. In fact, it has to be less than 10. So we're going to have to change that to 4.64, make it 10 times smaller, which means we make the exponent 10 times bigger. It becomes 4.64 times 10 to the 24th formula units. Stoichiometry allows you to take a balanced chemical equation and do some math on it. It's just mole math on one side plus mole math on the other with a ratio in between. In this case, it was only 2 steps. We started with the ratio and then we did some mole math on the other side. All right, candle wax. Candle wax is a weird thing. There's no real formula for it. There's a lot of different kinds of wax, and probably they're all mixed up in the wax. But we're going to assume we have a formula for the wax. We got pure wax of this formula, C21H44. Okay? 371.5 grams of candle wax. How many liters? So we're going to go from grams of wax to liters of carbon dioxide. So this is about wax and carbon dioxide, but we don't know the moles of wax or the moles of carbon dioxide. We have to do some fancy math. So first we're going to balance the equation. We're going to take this equation and say C21H44 combines with oxygen. Combustion always makes carbon dioxide and water. And back and forth and back and forth. You try to balance this. I'll stall for a bit. 21 carbon, we got a 21 on the other side. If there's 44 hydrogens, we got to put 22 oxygens. That means we're going to have 42 plus 22 is A lot. 42 and 22 is 64. So we're going to have 32 oxygens. Now, these are big numbers. The mole ratio here is 1 mole of wax and 32 moles of oxygen makes 21 moles of carbon dioxide plus 22 moles of water. That's the balanced chemical equation. That's our simple whole number ratio. Now, really, the numbers are kind of big compared to what we're used to, but wax is a pretty big compound. It takes a lot of oxygens and it makes a lot of carbon dioxide in water, but this is balanced and it can't be reduced. The question says, if you have grams of wax, how many liters of oxygen? We start on mass island and convert the mass of wax into moles using the molar mass. So here we go. That's our starting point. And we're going to take 371.5 grams of wax. Now, in order to convert this into moles, we need, look at the bottom right. What's the molar mass of wax? We got to do that. You got to, some scrap paper on the side. You have to write the formula, C21H44, and draw a line underneath it. C, then H. 21 times 12 equals, 44 times 1 equals, and add it up. Look what I got, 296 grams per mole. This is pretty big stuff. So the math problem, we have grams of wax. We're going to convert it into moles. The molar mass of this wax is 296 grams per mole. The grams cancel, so instead of saying 371.5 grams of wax, another way to say that is 1.255 moles of wax. Now we're looking at wax and carbon dioxide. So next step is going to be go through the mole ratio tunnel. We got to do the ratio of wax to carbon dioxide. So we're going to set that up next. The mole ratio between wax and carbon dioxide, it's in a 1 to 21 ratio. Let's make sure we know where these numbers come from. There's 1 mole of wax and it produces 21 moles of carbon dioxide. But in this math problem, we don't have a nice simple number like 1. We have 1.255 moles of wax. So we put that on the top of the mole ratio. And if 1 produces 21, 1.255 produces, we don't know how much. We got to cross multiply and figure this out. 1x is going to equal this. X equals, with 4 significant figures, 26.36 moles of carbon dioxide. All right, let's regroup. We started out with a certain chunk of wax. When it burns, it's going to produce carbon dioxide. The question is, if you have this many grams of wax, how many liters of carbon dioxide is going to come out? We have to do 3-step stoich. The first step, convert the mass of wax into moles. We did that in red. The second step, which is in purple, is to compare the ratio of moles of wax to moles of carbon dioxide. The balanced equation is 1 to 21. We have 1.255 moles to X. We cross multiply and we see that 1.255 moles of wax will produce 26.36 moles of carbon dioxide. Now we have to convert that number into liters. So we're going to rewrite that, bottom in red, 26.36 moles of carbon dioxide. And to go from moles to volume, we know that 1 mole of any gas, even carbon dioxide, is 22.4 liters. The moles cancel. And this comes out with 4 significant figures to be 590.5 liters of carbon dioxide. I know you don't care about this. I know that you think this is not important. But I'm telling you how important this is. Science has taken hundreds of years to figure out formulas, to figure out molar masses, to figure out the proportions and the balanced chemical equations. And now, in 35 minutes, you can do the craziest math in the world. That was impossible. 100 years ago, they couldn't, well, maybe 150 years ago, couldn't even do this. Couldn't do it. You're bored already. It's so easy. You got a good map. Don't get eaten by the shark. Step by step. Go slow. We got a couple more to do. We're going to use the same equation. There it is, right in the middle. Balanced chemical equation. Here we're going to say we're going to use up 23.9 moles of oxygen. How many moles of water form? Now this is easy. Moles to moles. We're not doing any conversions. It's just about the moles to moles. It's a mole ratio, 1-step stoich problem. Now in this balanced equation, the moles of oxygen compared to moles of water, well, look at the balanced equation. 32 moles of oxygen is going to produce 22 moles of water. So it's going to start out 32 to 22. But in this case, we have 23.9 moles of oxygen compared to X. How do we solve this? We have to cross multiply and then divide. 32X is going to equal 525.8. We divide both sides by 32. And we're going to get 16.4 moles of water. I'm teasing the water, right? So sometimes stoichiometry, from the balanced chemical equation, we're just going to compare moles to moles. One step. Sometimes it's 2 steps, and sometimes it's 3 steps, and it's harder. All right, the last thing I'm going to say, this is a great picture. This picture, every time I see it, every single year I use this picture. This picture, it looks so good. The water looks so cold. The water's splashing into this nice tall glass. It makes my mouth water. I wish I had that glass of water. All right, we're done with this class. You have yourself a swell day. Take a rest. All right.